Welcome back. So in the early lectures, we discussed about root locus and the introduction to root locus, and we looked at the control systems problem, and then also we looked at complex representation or vector representation of complex numbers. Now in this lecture, we are going to look at root locus definition. So definition of root locus. Okay, so given the block diagram below, given the block diagram for a closed loop control system below, it's a unity feedback system with a pure gain K and another gain, so this K1, another gain K2 over S into S plus 10. Okay. Our task then is to find an overall transfer function. So first we find the overall transfer function, which is K over S squared plus 10S plus K. Okay, this is the input, this is the output, where K1 times K2. Now, as we have discussed before, we can note that the closed loop poles change as K changes. So changing the gain is going to change the closed loop pole locations. Okay, so for example, we can select values for K as example, selecting K equals 0, 5, 10, 15, and so on and so forth up to maybe 50. Okay, then for each of the values of K, we can find, okay, the closed loop poles, okay, and plot them on the complex plane or complex axis. Okay, so for each value of K, we substitute into the transfer function here, and then we find the poles. Okay, and then we are going to plot that pole, which will be a complex number most probably, or a real number, or even purely imaginary number. You're going to plot that on the complex plane. Okay, now when we do this, then the graphical representation of the path of the closed loop poles as K varies from 0 to infinity is called the root locus. So the graphical representation that we'll get after we have plugged in series of values of K and evaluated or calculated the poles for each of them and plotted that representation, or that plot, is what we call the root locus. Okay, so of course I mentioned that k runs from 0 to infinity. You can actually have k running from negative infinity to negative infinity, or negative infinity to 0, or in fact any range of values of k. You can define the root locus for that. But in this class, okay, so we will concern ourselves in this class. We will limit ourselves to k greater than or equal to 0. So when we talk about the gain, we're only talking about positive gains, okay, 0 or positive gains. Okay, now if you remember, in our previous lecture we discussed, or we noted, that the poles the poles of a system, and especially we talked about first and second order systems. Okay, we noted that the poles of the second order system or first order system will be represented by S equals sigma plus j omega d if it's under damped second order system, where we said sigma equals zeta times omega n, that's the damping ratio times the natural frequency, and damped natural frequency or damped frequency of oscillation is given by omega n times square root of 1 minus zeta squared. Now we also define our Ts, which is the settling time, to be 4 over omega n, and this is an approximation for the settling time. We said our percentage overshoot equals E minus tilde pi over square root of 1 minus squared zeta squared, and we also said our peak time is given by pi over omega d, which is therefore pi over omega n square root of 1 minus zeta squared. So with this, then, it is obvious from what we have stated about the root locus that if changing k changes the s equals zeta plus j omega d, and of course it doesn't have to be the zeta can be the sigma can be 0, in which case we have purely imaginary pole, which means there is oscillation, or the omega d can be 0, in which case we have an overdamped system, and in case the sigmas are the same, and omega d is 0, then that one we have critically damped system. So we can have that scenario also. But looking at the discussion ahead, it is evident that if we change k and that changes sigma and or omega d, then the parameters, so changing k can change sigma and omega d, implies that you can change the damping ratio or change the natural frequency when you vary k. And if you change any of these, then that also implies that any quantity that depends on them will also change. So for example, if we change the damping ratio, if damping ratio changes by changing k, then it means our Ts, our Tp, and our percentage overshoot will change. Now if omega d changes by changing k, then it means that our TP, well, let me make it omega n. If omega n changes by changing the k, then it means that changing k will change our TP, and then it will also change our TS. Okay, so this is some information we have to know. And besides, okay, if changing k moves the poles from the left half plane to right half plane, then changing k affects the stability of the system. Okay, so this is another thing we have to be aware of. Okay, another thing we can state is it means changing k can change the response from, for example, overdamp. That's when all the poles are on the real axis, to critically damp. Repeated roots on the real axis to underdamp. Okay, so that is something that can happen to the system. Okay, so the system we have above there, let's for example look at if we are to plot the root locus, what we will get. Okay, so this is what is going to happen. When we have k equals 0, our roots will be here. Okay, one root will be there, and then we'll have another root. Okay, so let's go back to look at the expression we had. Okay, s squared plus 10s plus k. Okay, so if you have, so the expression is s squared plus 10s plus k. Okay, so if you equate this to 0, if k equals 0, then you have 10 s squared plus 10s equals 0, and therefore s into s plus 10 equals 0, s equals 0. Okay, and s equals minus 10. Okay, so those are the two. We can locate them here. Then we change k to 5. K equals 5. The equation becomes s squared plus 10 plus 5 equals 0, and therefore our poles will be 1, 2 equals minus 10 plus or minus square root of 10 squared minus 4 into 5 all over 2, and that is going to give us minus 5 plus minus, and then of course square root of 100 minus 20. So minus 5 plus minus square root of 80. Okay, so you can evaluate the square root of 80. Okay, and you do that, you are going to get for the plus, you get a value here, and then for the minus you get a value here. Then you can make your k equals 10. The expression becomes s squared plus 10s plus 10. Okay, so you evaluate that, you're going to get this and that as your poles. Then you make your k equals 15. You get s squared plus 10s plus 15. You find your poles. That's going to give you minus 8 and minus 2. So we can easily evaluate that one. So s1, 2 equals minus 10 plus minus square root of 15 squared minus 10 squared minus 4 times 15 all over 2. Is that what we get? Oh, okay, so let's do that for ten. Okay, so of course, yes, so 15 squared, no, 4 times 15, and you can evaluate that. So you keep evaluating these values, okay, and then you find it for when s equals 20. So s equals minus 10 plus minus square root of, then you get 10 squared minus 4 into 25. Okay, 1 is equal to 25 over this, and that will give you minus 10, okay, plus minus 0, and that's going to give you minus 5. Okay, so in that case we come here, you see that minus 5, it's a repeated root, so there we will have what do we have there? We have a critically damped system. And then right after that, you see that we move into, when we put 30, we get complex root conjugates. We put 35, complex conjugate, 36, complex conjugate, and 40, 45, then 50. Okay, so if we plot this, you will see that one of the poles started from the minus 10, then it was moving towards the 0. Another one started from this pole and it was moving towards the minus 10, and then the two of them seem to have crashed here, and each one moves up to infinity. This plot is what we call the root locus. Okay, so then what can we even say about this, looking at the plot? Okay, yes, we can make a lot of deductions about this plot. For example, we can say that the system is stable for all values of k. So you see that the root locus, okay, it starts from here, which is more like marginally stable system, and then for varying, with the exception of k equals 0, every other value of k pushes the roots into the left half plane, and it stays there forever. So you can vary k from 0 all the way to infinity, and all your roots are always going to be in the left half plane. Okay, this means that if you have such a system, and for example you have something that you use to increase a knob that you're using to increase the gain, purely pure gain system is a system like an amplifier, just for adding more energy to the system. So it means that if I turn on the gain, it is not in any way going to get into the unstable region. Okay, so this is always stable system. 2, you can make the deduction that for values of k less than 25. Okay, so if you see here, all the values of k less than 25, okay, you see that the two poles will all be on the real axis if k is less than 25, which implies the system is overdamped. 3, third deduction we can make, okay, is that when k equals 25, what happens? When k equals 25, what happens? Your guess is as good as mine. The system will be critically damped. Okay. And then the last thing we can also say will be what will happen when k is greater than 25. For k greater than 25, we will have an underdamped system. Okay, so when k is greater than 25, we have underdamped system. Okay. Now let's focus on the underdamped portion. So the underdamped portion, we'll talk about this portion. Okay, the values of k for which we have this. So this portion. Okay. So if you focus on the underdamped portion, so okay, what can we say about the TS, the percentage overshoot, and the TP for the system? Well, we can look at what happens. Okay, so 1, we can say that as k increases, okay, as k increases, you will see that your sigma equals remains constant. And so what can you say then? It means that TS equals 4 over sigma, or 4 over also remains constant. So as your k increases, for this particular system, as the gain increases, the settling time remains the same. Okay, so we are not going to in any way affect the settling time for the system. The second thing we can deduce about the underdamped system is that as k increases, what will happen to, you will see that the also the omega d, which is equal to okay you see that omega d increases. Okay, so from this we can see that our theta, okay, so we say 1 minus equals omega d over omega n squared. Okay, so basically if you are increasing, okay, so your theta square equals omega d over omega n. Okay, basically 1 minus that squared. Of course, you know that this is equal to tilde. Okay, so let me just take that off. Okay. So basically what we are trying to say here is, as let me take this off. I think we can deduce from here. As k increases, our tilde is going to reduce. Is it going to reduce? Yes. Let's prove it from the angle perspective. Okay, so you see that, let's take 3 points. One is this, one is that, one is that. Okay, omega. Okay, so it makes sense. You can easily see that theta 1, theta 2, theta 3. Okay, as k increases, the angle is going to increase because the imaginary part is increasing, and if you increase the angle, then for cos theta, okay, if the angle theta increases, then the cos theta will reduce, and that implies that your zeta square will reduce. So what I'm just trying to say is that when we increase the k, you automatically decrease the tilde, and when you decrease the tilde, then what happens to the percentage overshoot? Well, as you can see from the formula we stated, if you decrease tilde, okay, then the percentage overshoot is going to increase, because the portion, so you go here, okay, so we didn't state the formula, but I think we stated it earlier. Okay, so if we increase tilde, then this is going to actually also, decrease. If you decrease this, then this factor is going to decrease, and therefore the negative, because of the negative, it will be 1 over a smaller number, so that will cause an increase. Of course, you see that if we decrease that, then we also decrease, if you decrease this, you are increasing the denominator. Okay, so that is another factor that is going to help for us to increase the overshoot. So looking at that, it means if k increases, then tilde reduces or diminishes, and therefore our percentage OS will increase. Okay, the third deduction we can make is that if we increase k, then we are also increasing omega d, and that means we are reducing TP, okay, the peak time. So these are some deductions we can make from just merely plotting the root locus that we see here. So if you see the root locus, that alone gives you information that this system I'm looking at right now is stable for all values of k, and this system I'm looking at now for values less than 25 is going to be real roots. Yeah, and so increasing k will increase omega d and therefore reduce the peak time. So those are conclusions we can draw by just looking at the root locus plot. Okay, so we are going to end here, and next we'll look at the properties of the root locus. Okay, so thank you very much.